Okay, variation functions. So today we're going to look at all the different types of variation functions. There's direct variation and inverse variation and joint variation. Those are the basic three that we're going to be looking at. And so this is basically a review of what we have done in the past with all the different variations that we've worked with. First of all, direct variation is a form of a linear model, and it is a relationship where x and y can be written in the form y equals k times the value of x. And whenever you see this, see the k here, all right, that k is called the constant of variation. Right? So when we're talking about direct variation, that it's going to say y equals kx, and that means that y varies directly as x does. Which, in other words, since it varies directly, that means it does the same thing. So as y is getting bigger, then x is getting bigger. As y gets smaller or as x gets smaller, then y gets smaller. Okay? So they vary directly. So that it actually is in the form of a linear equation, similar to y equals mx plus b, except b has to be 0 for it to be a direct variation. Okay? So all we have is, that means with direct variation, then it goes through the origin, the graph does, and it just depends on then what is the slope, which is the value of k then. Okay? So writing and graphing direct variation problems, okay, you're always going to, if it's direct variation, it's always going to say that y varies directly as x. So they tell us that y equals 27, x equals 6. Write and graph the direct variation function. Well, for direct variation, we know that y equals k times x. And to be able to write the function, then, we need to know what the value of k is. And so in this problem, they tell us what y and x are, so we can use those to find the value of k. So we plug in 27 and 6 for y and x, and then solve it. And so this is 9 over 2, or if you want a decimal, 4.5. So then we would say that y equals 4.5x. That would be our direct variation function. So we could write it as, if we wanted to, we could write it as f of x equals 4.5x because it's a function. And then when we want to graph it then, the graphing of this is just a line, right? It has a y-intercept of 0 because all direct variation have y-intercept of 0. And it has a slope of 4.5. And so we just draw our line then through it. So direct variation function, need to know the value of k so we can write the function. All right, the function rule, y equals 4.5x. And then to graph it, we just have a nice straight line through the origin with a slope of 4.5 in this case. And with direct variation, the slope, or the constant of variation, k, can be positive or negative. Okay, can be both. Now, when you want to find specific values for a direct variation problem, you can solve for k and then use substitution, or you can use the proportions derived below. So we have two things for direct variation. We have the function rule, which just says that, so for direct variation, we have the function rule, y sub 1 equals kx sub 1, or y equals kx. And if we're trying to solve a direct variation problem, then we can use the direct variation proportion, which has y sub 1 over x sub 1 equals y sub 2 over x sub 2. So notice that this proportion I have, the y's are both in the numerator, the x's are both in the denominator. Okay, so we have this problem, the cost of an item in euros, E, varies directly as the cost of the item in dollars, D. And E equals 3.85 euros when D equals 5. Find D when E equals 10 euros. So you can do this two different ways. One method we can use, we can start out and we can find the value of K. And then the other method is we could use the proportion. Right, so we'll take a look at both of them. So first of all, they tell us that E varies directly as the cost of the item D. That means that E is going to equal K times D. Because it says varies directly. Okay? So the constant of variation is going to be here. So when I have 3.85 euros, I have $5. So I can find the value of K and then use that to find how many dollars 10 euros cost. So we divide this by 5, and K equals the wonderful number of what? What? 0.77. Is that an exact value? Okay. All right. So I know that the constant of variation is 0.77. So I can use that with the fact that when E equals 10 euros, then how many dollars is that? So put 10 back in for E. We know that K is 0.77, and we want to find the number of dollars for that. And once again, just some division here, 0.77. And if they have 10 euros, how many dollars is that? Okay, so approximately $12.99. Okay. All right. So that's one method of doing it. Okay. The other method of doing it is by using a proportion. And you'll probably find that using the proportion method is probably easier, a little bit quicker, because you just set up a proportion, then we cross multiply. Okay. So we'll set it up, first of all, that when it's a proportion in a direct variation proportion, then it is set up in this manner here. Like y1 over x1, x sub 1 equals y sub 2 over x sub 2. So except we're using euros and dollars. So it doesn't matter which one's in the numerator and which one's in the denominator in reality. Okay? In reality, it doesn't. Okay? But when we say that something varies directly as the other thing, then we're always going to put that first thing is always going to go in, should go in the numerator. Because these two things, and you don't need to write this down, but both of these things each represent the value of K. All right. So the one thing is that since y equals kx, well then that means that k equals y over x. So then if I do e sub 1 over d sub 1 or e sub 2 over d sub 2, it doesn't matter. They both are equal to k. So I can use those. Well, now this is actually turns into a little bit easier problem because all I need to do is plug in what I know. When I have 3.85 euros, it costs $5. If I have 10 euros, how much does it cost? So the properties of a proportion, we cross multiply. Get 3.85d equals 50, because we're going to multiply, or cross multiply them. So we should, when we divide by 3.85, we should still end up with 12.99 approximately. So it really doesn't matter which method you use. Those will both get you to the right answer. I prefer the proportion method, and I would figure that probably most of you would probably end up doing it that way too. All right. So there's the direct variation. Okay. Let's look at something called joint variation. When joint variation, it's a relationship among three variables that can be written in the form of y equals k times x times z, where k is still that constant of variation. And in this case, then, if it says that y varies jointly with as x and z, so if it says it's varying jointly with two other things, that means then we're going to have the formula that y equals kxz, or have this thing varies jointly with these two things, so it'll be this thing equals k times these other two. So the volume of a cone varies jointly as the area of the base and the height. Okay? So here it says, so V varies jointly as the area of the base and the height. So that tells me that it's varying jointly, so it's joint variation. So V equals K times BH. So when the volume is 12 pi, the base is 9 pi, and the height is 4. Now there is no proportion for joint variation. Okay, you can't use a proportion for that. Wait, well, I guess you could, but we're going to do it this way. Right? So we divide. What's 4 times 9? 36. Now when they give you pi in an equation like this, okay, then just leave it at, use it as pi like you would like an x or a y or something like that. Okay, don't think of it as a, don't put 3.14 in for it. Okay? Okay. So we'll divide by 36 pi. So we get that k is equal to 1/3. Nope, because the pi's are going to cancel. because there's one in the numerator and in the denominator. So now if I rewrote the joint variation, then I could say that V equals 1/3 BH, because we just found out that the constant variation is 1/3. Now if I'm offered any other scenario like this, I know what K is. So they says if V is 24 pi, we know that K is 1/3, the height is 9, they want us to find the base. What's 1/3 times 9? 3. Okay, so I'll simplify that side. 24 pi equals 3b. And if we divide by 3, then b equals 8 pi. Now they tell us that, so is this just 8 pi, or are there some units to go with that 8 pi? Okay, so what are the units to go with it? You mean square feet? Okay, so this would be 8 pi, so b equals 8 pi square feet. Because, and here's the thing, it says the area of the base, okay, the area of the base. Area is two-dimensional, right? Okay, so that would be square feet then. The other main type of variation is called inverse variation. Okay? With the inverse variation, as x increases, y decreases. As x decreases, y increases. So if they're inverse variation, that means they vary the opposite way. Okay? So that general formula for inverse variation is y equals k over x. And we would see it as y varies inversely as x does. Now I got too many yellows in there. Okay. So y equals k over x, which means y varies inversely as x does. Okay. So it'd be like speed, time, and distance. We would multiply speed times time to get distance. Okay. But to be able to get distance, or be able to get one, when I know the distance, then I have to do some division. And inverse variation is using division. So where direct variation was a linear model, inverse variation is, it's an inverse variation model, but it's a rational function instead. And we'll see what the graph of those look like here in a second. So it says given, and this is the first thing you always want to do, is recognize what's it talking about, what varies how with something else. And here it says it varies inversely. So as soon as I see that inversely, I know that it's going to be y equals k over x because of the inverse. So they tell us when y equals 4, x equals 5. Well, how do I find k then? Let's come to a general knowledge about k. So if y equals k over x, then to find k, we're going to multiply x and y together when it's inverse variation. When it's direct variation, we're dividing them. When it's inverse variation, we're multiplying them to get k. So we put 4 in for y and 5 in for x, so that k is equal to 20. So my function is y equals 20 over x. So the graph of this then, okay, is all inverse variation models, or y equals k over x. The parent function is y equals 1 over x, which has a graph that looks like this. Except I just did that wrong, so. Oops. Y equals k over x, which means that it's going to be in the first quadrant and the third quadrant, not the second and fourth. Okay. When will it be in the second and fourth? Okay, yep, when k is negative. Okay. Okay. So this was the parent function, y equals 1 over x. Okay. Well, what's the difference between y equals 1 over x and y equals 20 over x? 19, okay? All right, that's true to a certain extent, but what it is it means that it's stretched out 20 times bigger. Because the value in the numerator is 20 times bigger, so it's stretched out 20 times bigger. Well, let's figure out the graph of this then is going to look like this, except I'm just going to need to be able to, I can plot some specific values to help me with this. All right, so let's put in some couple negative values. Let's pick some really easy ones to work with. Okay, what are the factors of 20? What are the factors of 20? Okay, we can do 4 and 5, right? Or we could do 2 and 10, okay? All right, so let me make it a little bit bigger. Okay, so if x is negative 10, y is negative 2, right? If x is negative 5, y is negative 4. If x is negative 4, y is negative 5. And if x is negative 2, y is negative 10. Or we would use those same positive values. 2 and 10, 10 and 2, 4 and 5, 5 and 4. This graph ever going to cross the x-axis or the y-axis? No. So when I draw my graph, it looks like this. You love how I make perfect graphs like that. I should get paid extra for having those perfect graphs, shouldn't I? No? Okay. All right, so we graph inverse variation function, use values of x that are factors of k, so your y values will always be integers, and it's much easier to graph them. Okay? And your graph should be very close to exact. It doesn't have to be perfect, but you can't just walk up here and say, oh, all right, it's inverse variation, so let's see, it looks like this, and it looks like that. All right, great, perfect graph. Okay, no, you got to have a little bit of, exactness to it. All right, so there's the inverse variation. So direct variation, y equals kx. Joint variation, y equals k times x times z. And then with inverse variation, it's y equals k over x. All right. Now, if we want to solve an inverse variation problem, when we have inverse variation problems, the formula that works out is a little bit different. So an inverse variation problem, we have, instead of having a proportion, we basically have a product that x times y is equal to x times y, because what did we figure out? We figured out that k is equal to x times y. So both of these values here then would be equal to k. So I can say y sub 1 times x sub 1 equals y sub 2 times x sub 2. Okay? And it's much easier, and we're not even going to do method 1, we're just going to go right to method 2. Method 2 is much easier just because it's you set it up, you got everything right there, and you solve. Or if you use method 1 where you got to find k first of all, then you got a little bit more work involved to it. So this is for when it varies inversely. So time t needed to complete a certain race varies inversely as the runner's average speed. So time varies inversely with their average speed. Okay? We're always looking for how does it vary? Okay, does it vary directly? Does it vary jointly? Does it vary inversely? Since it says inversely, then we can use this method here for solving an inverse variation problem. It says if a runner's average speed is 8.82 miles per hour, they complete the race in 2.97 hours. So 8.82 times 2.97 equals, what is the average speed of the runner who completes the race in 3.5 hours? 3.5 times s for speed. Make sure your 5's and s's don't look alike. And that's just a matter of dividing. So their time is approximately 7.48. Oops, this is their speed. I mean, their speed is approximately miles per hour. 7.48 miles per hour. So here's a big question for you. How far did they go? How far did they travel? Well, let's see, they're running, so how far did they run? What? 26.18. How'd you get that? Okay. Or 8.82 times 2.97. What do you think that was that they ran? A marathon, yep. Okay. So not only was this person running, they had a specific thing reason they were running in a marathon. Okay. All right. All right. You okay with that then? Okay, let's get. All right, so we can use algebra to rewrite variation functions in terms of k. So we talked about this as we're going through, so let's look at it a little bit further. We have direct variation. Okay. All right, y equals k times x, which means that k is equal to y over x. Or inverse variation, y equals k over x, so k equals x times y. So we have, for direct variation, we have a constant ratio, and for inverse variation, we have a constant product. So knowing those two things allows me to take a set of data and determine whether it is direct variation, inverse variation, or neither. So if they have a constant ratio or they have a constant product, then they're direct variation or inverse variation. If they don't have either one, then they're neither. And lots of times you can look at them and you can figure it out by just looking at them. Not always, but sometimes you can. So what I want to do is I want to find out our, if I do y divided by x, do I get the same value? Or if I multiply x and y, do I get the same value? Okay, those are the two things I'm looking for. So let's see. Let's look at the division, though. 8 divided by 6.5, is that the same as 4 divided by 13? Let's see. 8 divided by 6.5 is over 1, right? Okay, I'm dividing them. And 4 divided by 13 is less than 1, isn't it? So these are not division. Okay, right? If I multiply them, are they the same then? Okay, that's what you meant, right? Okay. All right, 13 times 4 is 52. 104 times 0.5 is 52. And 6.5 times 8 is 52. Okay? So when I multiply these together, they're the same. Right? Which means then that they are inverse variation. Okay? Well, let's look at the data for a moment, too. Right? What happens to y as x gets bigger? Okay, it's getting smaller. Okay? So that's an indication for us, too. All right, that as x gets bigger, y gets smaller, so it's probably inverse variation. So I check it by multiplying all the x and y's together, and they are the same, so it does represent inverse variation problem. Letter B. Okay, as x gets bigger, y is getting bigger. So that means that it could be a direct variation, but it can't be inverse. All right? So if it's direct variation, we can divide them. 30 divided by 5 is 6. 48 divided by 8 is, and 72 divided by 12 is 6. So because those are all the same, this is a direct variation. Because the constant ratio is 6 for each of them. Okay. So start by looking at the data. Okay. What happens to y as x changes? If y is getting bigger, then it's possibly a direct variation. If y is getting smaller, then it's possibly inverse variation. Okay. Letter C. All right. So as x is getting bigger, y is also getting bigger, right? All right. So that means it could be a direct variation. So let's look at the ratios. We get 5/3, 14 over 6, and 21 over 8. Are those equivalent? Okay. Well, first of all, if we have 5/3 and 14 over 6 is 7/3, and those two are not equal, so this would be a case of it is neither. Okay. So when they want us to figure out identify direct and inverse variation, first look at the table of values. As x gets bigger, does y get bigger? Okay. If it does, we're checking for constant ratio. If it doesn't, then we're looking for a constant product. That's 6. Wow, look at that. Did I skip one? Oh, you hit them all. Look at that. One more. Okay, number 7 then. Last thing, combined variation. Combined variation is a relationship that contains both direct and inverse. Quantities that vary directly appear in the numerator, and quantities that vary inversely appear in the denominator. Which that should make sense from what we just talked about. Because with direct variation, as x gets bigger, y gets bigger. Inverse, as x gets bigger, y gets smaller. So combined variation would look like y equals kx over y. Oops, over z, excuse me. Over z. Where it varies directly with x, because that's in the numerator, and inversely with z, because that's in the denominator. So we have this nice chemistry application problem. It says the change in temperature of an aluminum wire varies inversely as its mass m and directly as the amount of heat energy E transferred. Okay, so let's just start right there. It says the change in temperature of aluminum wire varies inversely with the mass, directly with the amount of heat energy E. So we've got change in temperature. Okay, so we'll use T for the change in temperature. Varies inversely with the mass, so that's in the denominator, and directly with the heat energy, that's in the numerator, and then we have our constant of variation. And that constant variation always is in the numerator. So it says the temperature, oh, and they're using I. I don't know why they're using I, but let's change that to a T. The temperature of an aluminum wire with a mass of 0.1 kilograms rises 5 degrees Celsius when 450 joules of heat energy are transferred to it. How much heat energy must be transferred to an aluminum wire with a mass of 2/10 of a kilogram? Raise its temperature 20 degrees Celsius. Okay. So let's recognize this. This says the change in temperature of aluminum wire. Okay. So it says the temperature of aluminum wire with a mass of 0.1 kilograms. So we have 0.1 in the denominator. Rises 5 degrees Celsius, so that's our change in temperature is 5 degrees. And when 250 joules of heat energy are transferred. So the energy is 450, and we need to use that information to find the value of K. So what do we do to find K then? Okay. So we have two options, don't we? Okay. We could simplify the right side of the equal sign first, take 450 divided by 0.1, or we could just multiply both sides by 0.1 and then divide by 450. Okay. It doesn't matter, so whichever way you're comfortable doing it, then you can do it that way. So I was going to multiply by 0.1 first, so that gives me 0.5 equals K times 450. And then when we divide by 450, we're going to get a really small number. K equals what? Point what? With a bar over the 1? Okay. So it tells us then that if How much energy must be transferred to an aluminum wire with a mass of 0.2 of a kilogram? So our mass is 0.2 to raise the temperature 20 degrees Celsius. So we know that K is point, we'll use 3 ones there just to get us some good value. So we need to find E. Okay, how much heat energy must be transferred? So this time I'm going to go ahead and once again multiply by 0.2 first. So we get 4 equals we get E equals what? 3,600. And that is in joules, right? All right, so we have 4 different things. All right, direct variation, y equals k times x. It's a linear relationship. X increases, y increases. Joint variation, y equals k times x times z. So where it varies directly with 2 things, basically, for joint variation. Inverse variation, as x increases, y decreases. So y equals k over x. And then we have combined variation where we're going to put all of them together. Right, so it's important that you identify which type of variation is happening first before you go on from there.